Hello everyone, welcome to today's lecture. So today's lecture is on discretization method. Today's lecture is on discretization method. So discretization method are used to convert partial differential equations to linear algebraic equation, which can be solved by numerical methods. So in many engineering and physics problems, we have non-linear equation. For example, in mechanical engineering, we have Navier-Stokes equation, heat transfer equation, and we also have, let's say, a structural dynamics equation which are non-linear structural dynamics equation, and we also have non-linear oscillator equations. So there are several non-linear equations which can't be solved analytically. So to solve them even by numerical methods, we have to convert those non-linear partial differential equation to linear algebraic equation. That's where the numerical methods comes in picture. So let's take an example. Let's say there is a heat transfer in a rod, and we consider three discrete points at any point in the rod, or let's say four discrete points. So basically, the discretization method tells us the relationship between the neighboring points, so that we can solve on those discrete points iteratively or by using any numerical methods uh, to get the solution. Okay, so basically there are three discretization method. First is finite difference, finite element, and finite volume method. So these three discretization method has their methodology to discretize the equation and their advantages and disadvantages. So basically finite element method is mostly used in structural dynamics. Let's say bending of the beam and all these things. Structural dynamics, and FVM is used in fluid and thermal engineering to solve Navier-Stokes equation and heat transfer equation. Although any of these methods can be used to solve any numerical problem, like any partial differential equation, but they have their advantages and disadvantages respectively. So we'll discuss. Now in this lecture, we'll focus more on. First, we'll discuss what is FDM, and we'll discuss the difference between finite difference method and finite element method. Then we'll discuss why FVM, that is why FVM is needed and what are its advantages. First, we fully understand the FDM and FVM. Then we'll discuss FBM, the basics of FBM, what is the discretization methodology for FBM, and along with this for FDM and FVM, we'll discretize 1D steady state heat equation, 1D steady state heat conduction basically in a rod, and when we'll also look at the algorithm and also code on MATLAB and see our results. So now first let's move on to the finite difference method and start the finite difference method. So we have FDM. So from now on, it's better to move with the example and learn everything with the practical approach. So for that, we'll consider 1D steady state heat conduction in a rod. All right. So we'll learn everything with the help of this example. So the equation for this is this. So we are considering conductivity K to be constant, and let us also consider the heat generation. S is heat generation. So for this problem, let's say we have a rod and temperature at the left boundary is T1 and temperature at the right boundary is T2. So this is the whole domain, and let's discretize or break this whole domain into several discrete points. And let's call this point as I, this point as I plus 1, and this point as I minus 1. So this and the domain is divided uniformly. So we consider the distance between the two neighboring points as delta x. All right, and this point is tx. This point is tx plus delta x, and this is tx minus delta x. So I am using the notations of I plus 1 and x delta x plus delta x to make things like synchronize in the algorithm and the coding part, so it will be easy for us to understand. All right, so the basic of finite difference method, as the name suggests, it works on the difference, finite difference. So this works like totally on Taylor series. So if you don't have the idea of Taylor series, just understand the basic, take any mathematics book, and just Greenberg is a good book. So just take it and understand at least the basic of Taylor series. So with the help of Taylor series, we'll move on. So what we will use Taylor series for this, and we'll write this. So basically in finite difference method, there are a lot of approaches, let's say, and there are a center difference, forward difference, and backward difference. So this is just the theory. Once you understand all of this, it will be everything will be easy for you to understand. So here we are using center difference. All right, just simply using Taylor series here, nothing else. This derivative is at I, because we are considering I to be the pivotal point for Taylor series, or kind of center point. So here in this equation we need the second derivative. So we'll just simply add these two equations. So this is simply why Taylor series, just look out for it if you don't know this. Let's just add these two equations, and let's write tx plus delta x as ti plus 1. It is simpler for us. All right, so tx becomes ti, and this will become 2 delta x square dx square dx d square t dx square. So we need this derivative. Okay, so we'll just rearrange some things and we'll get this. That is d square t dx square will be equal to, this is 2 here, plus ti minus 1. Just simply do this. All right, it's not much of a work. And finally we get this. That is so if we put this in this equation, right, this is the second derivative, we put this in this equation, we get k delta x square ti plus 1 minus t2 2ti plus ti minus 1 plus s equal to 0. So this is final discretized equation using finite difference method for this particular problem. So what this basically gives us? So this gives us relationship between neighboring point, that is I minus 1, I, and I plus 1. Now if we apply this equation, final discretized equation for this whole domain, what this will give us is the relationship between the points throughout the domain. And this is how we solve the equation and get the correct results, if we establish correct relationship between the neighboring points. That's how the iterative method works. So this gets out the relationship. All right, and this is it, that's it, this is the final equation. And now after this we'll use this equation to write the algorithm and code in the MATLAB to get the to solve the 1D steady state heat equation using numerical method. Now let's just take 2 minutes and understand the basic difference between finite difference and finite element method. So let's take, let's just assume that this is temperature and this is x. So the variation of temperature within this whole domain x can be anything. It can be any random thing. Let's say this like this. And in finite, the basic difference between finite element method and finite difference can be totally understood from its name. So what is the difference? E for element, difference for D for difference. So if we consider any 2 points, let's say here. So if we consider these 2 points, all right. So in finite difference method, we do not care about the profile that is between 2 points. So we just consider these as two discrete points, nothing else. But in finite element method, this is finite element method, the profile is important. All right. So if we consider linear profile, it will just go like look like this. All right. So if we are considering let's say quadratic profile in the element, so profile in the element, the piecewise profile in the element, this is the element between two discrete points. So the profile in between the element is most important. So if we are considering quadratic profile, we have to also include another point, infinite element I'm talking about. In that case, our profile will be like look like this, right? So we can always consider different profile. We can consider linear, quadratic, or we can even consider exponential profiles and solve according to that. That's why it is better to use finite element method in structural dynamics, in which the bending of a element is also important. What is the profile in element? So it is more helpful in, like, it is more intuitive to use finite element method in structural dynamics. So as we have derived the discretization equation using FDM, now we'll move on to the algorithm part and see the algorithm that we will use for the coding. All right. So here we'll discuss the algorithm. So we have this equation that we have derived, plus s equal to 0. Since k and delta x are constant, so we can consider there is a 2. We can consider this as a because it is a fixed. So if we have to iterate about ti, so we consider ti on the left and everything to the right. So if we kind of rearrange it, we will get ti is equal to uh, ti plus 1 plus ti minus 1 uh, plus s by a divided by 2. So this is the equation we'll iterate about. Okay, so this is s by a. So before we move to algorithm, first we need to consider, when we start to iterate, we have to first give the boundary conditions. So let us say we divide this in n discrete points. So this will be 0th point, or you can say the first point, and let's say the at left boundary the temperature is T1, and at the right boundary the temperature is T2. Also, when we start the algorithm, we have to use an initial condition, and we are calling it T naught, and let's say the initial condition itself is T naught. All right. So before starting the algorithm, we have to use two vectors. What is T old and one is T. So we have to give the we have to define two vectors T old and T, which have length of n. All right. So just let's jump to the algorithm. So what our algorithm says is, we use a while loop and we say uh, till the error between two successive iteration is greater than tolerance. Tolerance is the we have to solve till the error between two successive iteration like is less than tolerance, so that we can achieve the steady state solution. And so let's define tolerance here, something, let's say 10 is to minus 4. Okay. So we say till the error between two successive iterations, that is epsilon, is greater than tolerance, keep doing this. Okay, so first we have to like define the initial condition for t old and t, and then we also have to define the boundary condition. So we say t1 is equal to t1 and tn is equal to t2. So we have to use a for loop, and keep in mind that we have to iterate only from 2 to n minus 1 here, because the boundary points are already fixed, and we use simply just this equation, and this is, we say ti is equal to ti plus 1 plus ti minus 1 plus s by a divided by 2. So we iterate about this equation. So let's say we are currently moving in the 100th iteration. So we calculate. So I have done a little mistake here. That is, so here we are, this Ti is current temperature. So you have, we're going to use here old temperature. That is T old I plus 1 plus T old I minus 1 plus S by A is constant. We are also considering the heat generation here constant, although you can use a variable one. So what we are doing here, we are calculating the current temperature of present iteration, let's say 100, with the help of the temperature from the previous iteration, that is T old, that is 99th iteration, let's say. So first thing that we'll calculate after this is error, that is the difference. You can take it as relative, so that is difference between the temperature of old and the current iteration, and then you update the temperature. You say that old temperature is current temperature, so that when we move on to the next iteration, it considers the previous, like the previous temperature. So this is just kind of updation of the old temperature, and we go like this. So this thing will happen till the the error, that is epsilon, is less than tolerance. So the, as soon as the epsilon becomes less than tolerance, it will exit the while loop and it will give us the steady state solution. So this is the algorithm, and we are considering k by 2 delta x square as constant, that is a, and you can give any heat generation. So I hope it is clear. We'll just quickly jump to the MATLAB code and see how it works and how we can write this in MATLAB. First thing is define the geometrical parameter. Alright, let's say length of the rod is 1, conductivity is also 1, heat generation is also 1. Okay, then we'll divide the domain. Okay, so let's divide the domain in, let's say, 21 points, and that will give us the dx, that is the length between 2 points, as uh, L divided by n minus 1. So in MATLAB you can always print this. So if you don't put a semicolon, it will give you the values. So clear or closer, this is CLC. You see the dx is 0.051, right? And you also define x equal to from 0 to, with the difference of dx to 1. This gives us the discrete points in the domain. Now we initialize the temperature. So we define t as 0. So we want to define the vector. So for that we have to do this n comma 1. So we are defining a vector with endpoints, and zeros means we are initializing the temperature as 0. Alright, so next we define the error. So let's define the boundary condition BC. So temperature at first left boundary is, let's say, 273, and temperature at right boundary is, let's say, 373. And now we define the error is equal to 1, tolerance, let's say, is 0.001. Okay, now so we are defining error equal to 1, so that when we define the while loop and we say do this while error is greater than tolerance, so defining initializing e equal to 1 is because we want so that the code enters in the first loop of the first while loop. So error for the first loop, epsilon is also greater than like tolerance. So what we do is we just simply use for loop. We say for I equal to n minus 1. So we are not including the boundary point, that is I equal to 1 and n. We say t I equal to t old. We are just writing the discretization equation here s by a, and we are dividing by 2. Okay, so we have to define what is a. So we say a is equal to L divided by 2 asterisk ds asterisk dx. Alright, so it is L by L or K. I think K, it is K. Alright, so it is K by 2x. Okay, so we have defined a. S is our heat generation, that is capital small s. So now what we do is we do end it. The first thing we do after the for loop is calculate error. And just keep in mind we want the maximum in the whole domain. So what we do is max of absolute of. So we want only the positive value, absolute of the error, not the negative value. We have defined the error, then we update the t old is equal to t. Alright, so we update the t old to end, and then we can try to plot it, plot xt. Let's say how it works. Let's run it. Illegal use for. Okay, let's just move this bracket. Okay, so it works. Yeah, so you can see the temperature on the left boundary is 273, at temperature on the right boundary, that is 1, is 373. This is linear variation because s is very small. So s, if you put s equal to 0, we get linear. The temperature is linear within the rod. But if we try to increase the s, that is the heat generation, let's put it 20. You see, there will be a bending has started. That is the profile now seems to be parabolic. So now if we increase it further, let's say 500, you see, so this is the profile we get. Okay, and so that being totally parabolic with the heat generation. So now if we take uniform boundary condition at the left and right boundary, that is 273, the same boundary condition, then the maximum temperature due to heat generation should come at the center. You see, so the maximum temperature is coming at the center. I hope you have learned something from this video, and thank you for watching. See you again.